Okay, let's get started. So we're almost done with distributions. So last week we discussed some special classes of distributions, namely discrete and continuous ones. So the discreteness and continuity of the distribution is defined by its relationship with respect to some measure on the real line, for instance, a counting measure of a countable set, or the Lebesgue measure. So if the distribution of a numerical random variable is absolutely continuous with respect to some counting measure, with respect to some countable set, then we say this distribution is discrete, and indeed the distribution is a discrete measure, and all you need to know about the distribution is that is the probabilities assigned to specific points. Okay, the other extreme case is where your distribution is absolutely continuous with respect to the Lebesgue measure on the real line. And in that case, you have density, a Radon-Nikodym derivative with respect to the Lebesgue measure. And this density is the classical density that is used in undergraduate courses a lot, the so-called probability density function. But even in the discrete case, from our viewpoint, this is still a density. Density in the sense that it is a Radon-Nikodym derivative with respect to some counting measure. So for us, it is always a density, whether it is a probability mass function or a probability density function. We can always say it is a density, but in the more traditional and elementary setting, the densities are for continuous random variables, and for discrete ones, you look at point masses. Okay. So just to avoid confusion, I will try to say Radon-Nikodym derivative instead of saying just density as much as possible, just to avoid such a confusion. Okay, so today we're not going to look at any special distributions anymore, so we're done with that. Instead, we're going to look at some certain transforms that characterize the distributions of random variables. Okay. So there are three types of transforms I'd like to discuss with you. So the first one is for discrete random variables, and it is called the generating function. Okay, so let's say let's call it transforms. Okay, so suppose you're on a probability space with some numerical random variable. And let's say X has distribution nu. Nu is the distribution of X under P. So the first type of transforms we're going to discuss is generating functions. So it's not moment generating function. It is just generating function. And for this, we're going to assume, so suppose X takes values in the set 0, 1, 2, etc., and maybe sometimes you allow for plus infinity, almost surely. So this is a discrete random variable taking values in the set, okay, positive integers, and also the plus infinity is allowed, okay. So if you look at such a random variable, and you take a number between 0 and 1, okay, if you look at z raised to power x of omega, so x of omega is going to be 0, 1, 2, etc., or plus infinity. So this is going to be a number, again, between 0 and 1. Of course, we need to make some conventions about maybe 0 and infinity. So if z is between 0 and 1, 0 included, 1 excluded, then we're going to define z of infinity to be 0. And if this is 1, we're going to define z of infinity, z to power infinity as 1. And this is just as a limit, right? So if you look at z to power n for some finite n, so this is getting smaller and smaller, and in the 0 case, this is always 0. So why not set it this way, right? And in the 1 case, 1 to power something is always 1, so why not define z to infinity as 1? Of course, in other areas, in other situations, in mathematics, maybe this is a problematic convention, but we don't care. Okay? So the point is that z to x is, let me say this way. So z to x is bounded by 1. It's always positive, so let me just write this way. Almost surely, right? So this is a bounded random variable, almost surely bounded random variable. And if it is bounded by 1, this means its expectation is also finite. Let me also put 0 here. So it's a random variable between 0 and 1, so its expectation is also between 0 and 1. Okay, we're going to call it g of z, okay, is a number between 0 and 1. So this function g from 0, 1 to 0, 1 is called the generating function of x, or the generating function of the distribution of x. So what is nice about this generating function is that it is not very difficult to calculate, because x is a discrete random variable. So if you look at this g of z, it's expected value of z to x. So x is 0, x is 1, sorry, yeah, x is 0, or x is 1, or x is 2. So we're going to look at all those cases. So z to power n times the probability that x is equal to n, where n is running in z plus. So 0, 1, 2, 3, etc. But there is also z to infinity. Z to infinity times the probability that x is equal to plus infinity. So you have the positive integers and also maybe plus infinity sometimes. So if you'd like to write it in an explicit way, well, so z to power 0 is 1, right? Times x is equal to 0. So this is z to power 0. Now, z to power 1 times x is equal to 1. Z to power 2, x is equal to 2, etc., etc. And there is z to power infinity, x is equal to infinity. So this is not a polynomial, but for instance, if your random variable just takes finitely many values, okay, let's say after some point the probabilities are all 0, like a binomial random variable or some kind of a random variable with finitely many possible values, then it's going to be a polynomial. And even if it's not, it's a limit of polynomials. So you can check g is infinitely differentiable. And it is indeed not very difficult to calculate the derivatives, right? So if you look at g prime z, okay, the first derivative, so this is going to disappear, and we're going to have probability x equals 1. Now what? 2 times z times, so let me write z times 2 probability x is equal to 2. So we have z cubed, which gives us z squared times 3p x is equal to 3, etc., etc. So what is nice about this G or G prime? So what if I let Z equals 0? What happens? What is G of Z, G prime of Z 0? The first term, right? How about here? What is G of 0? Well, this is going to give us 0, right? 0 to infinity is 0. So this is going to disappear. And this is going to be what? Probability that x is equal to 0, because the other terms will just go away. So we have G of 0 equals probability x is equal to 0. G prime of 0, probability x is equal to 1. Let's do it one more time. So G double prime is, now this is going to disappear, and we're going to have 2 times probability x is equal to 2. Z times 3 times 2 times probability x is equal to 3, etc., etc. So if you look at G double prime of 0, you're going to get 2 probability x is equal to 2, or probability x is equal to 2 is G double prime 0 over 2. So in general, you can keep doing this. So in general, probability x is equal to n is given by G nth derivative at 0 divided by n factorial. Second derivative divided by 2 factorial. First derivative divided by 1 factorial, etc. Okay? So for n z plus, okay, and I just assume G of the 0th derivative is G itself. Okay? And if you know those probabilities, you can also calculate the probability that x is equal to plus infinity, if there is any probability left for this. So it is 1 minus all those probabilities, x is equal to 0, 1, 2, etc., etc. So G nth derivative 0 over n factorial. So that's why we say, so G characterizes the distribution of x. Because you know all those probabilities. If you know G, you can calculate. So let's calculate G, for instance. Let's say x is Poisson with C, okay, where C is some positive number. So remember, this means x is equal to n is e to negative c, c to n over n factorial for n 0, 1, 2. Now we don't have plus infinity. So now what is expected value of z to x? Well, z to n, e to negative, let me write it this way first, x is equal to n, right? This is how we calculate this expectation. So 0 to infinity, z to n, e to negative c, c to n, n factorial. So this is like what? E to negative c, zc to power n, and n factorial. Let me get rid of e to negative c here, okay? Let me write it this way, so that this is equal to e to zc, right? E to zc. So this is equal to what? Minus c, 1 minus z. This is g of z. Okay, so this is the generating function for Poisson. So you can just do what we did. You can just calculate its derivatives and see that you get those probabilities, okay, by this formula. So for such discrete random variables, I mean, once you see that the generating function has this form. Somewhere you must have some table of generating functions, right? Maybe you check it from Wikipedia, or you have some textbook listing those well-known generating functions. So one way to prove that some random variable is Poisson is, for instance, to show that its generating function has this form. Okay? Maybe you cannot directly calculate this probability, but somehow you have a way to calculate this generating function. So in that case, if you come up with this formula, if you come up with this result, then you would recognize that, hey, this is the generating function of the Poisson, so this must be a Poisson distributed random variable. So it's a technique, proof technique, okay? So if you want to show that some random variable is Poisson, maybe you can use this technique, okay? Doesn't mean that it always works well, but sometimes it's convenient. Sometimes it's convenient. So if you know the distribution of x, you know the values of g, right? Because this is calculated, right? If you know the distribution, you can calculate this expectation. So you calculate g. G has this formula, okay? If you don't know the distribution of x, but you know the generating function of x, then what you can do is to differentiate it and calculate this quantity for every n, as well as 1 minus all those probabilities. So you're going to get the distribution of x. Okay? So it is really 1-to-1. Okay? If you know the distribution, you can calculate the generating function. If you know the generating function, you can calculate the distribution. And the way to calculate the distribution is very concrete, just through differentiation. Okay. Any questions? Okay. So this is used a lot, for instance, in the theory of branching processes. So branching processes are certain stochastic processes looking at, for instance, the number of individuals in a family. Okay? You have a family tree, you have the first generation, you have the second generation, and you're interested in the number of people in each generation. And there you model it as a Markov chain and calculate some quantities using generating functions. Because there the number of individuals is 0, 1, 2, etc., right? It's a discrete random variable. So using generating function is convenient in such a situation. Okay, so this was number one. Number two is Laplace transforms. Okay, so now we're going to assume, suppose x is positive, okay? But not necessarily discrete. It can again take the value plus infinity, and it can take the value 0 and everything in between. So we just want to come up with an integrable, maybe even bounded random variable that is attached to x, okay? So one way to do it is to look at the exponential function. So if you look at the exponential function, let's say e to negative x, okay? So this is x, let's say x, and e to negative x. If you look at e to negative x function, this function is very nice on the positive real line. Because at 0, this is just 1, right? E to negative 0 is 1. And as x increases, minus x decreases, then e to minus x decreases, with the limit being 0. This is always a positive quantity, so it's between 0 and 1. And at x equals plus infinity, you really have the value 0. I don't want to write it as a line. Let me just put a point here, okay? Outside the real line. I put an additional point to denote x is equal to plus infinity. And this is even the same thing if you Rx for some R positive. the picture doesn't change much. Just the derivatives, just the rate of decrease is changing when you change r, but the picture is pretty much the same. So if you have, again, x equals 0, you just have e to 0, which is 1. So e to negative rx is always a number between 0 and 1. So you can safely apply it to a positive random variable, and that's going to give you a random variable between 0 and 1. So if you have r that is positive real number, okay, and we know that x is between 0 and plus infinity, okay, let's say x of omega, then we have e to negative r x of omega between 0 and 1. Of course, it takes the value 0 if and only if it's plus infinity, but that's fine. So this function is even invertible, right? It's 1 to 1, and you can find its inverse on this interval. On this interval, its inverse is well defined, just negative log. Okay. So again, you have a number between 0 and 1, a random variable between 0 and 1. So the expected value is also between 0 and 1. Okay, for every r. So we call this function, so as a function of r, okay, so r is taken from positive real line, and it maps to e to negative rx, which is between 0 and 1, is called the Laplace transform of x, or that of the distribution of x. Of course, how do we calculate it? Well, that's just a function of x, so e to negative rx, and then the distribution of x. And since the distribution is over r bar plus, so you can calculate it by an integral like this. So maybe we can just solve an example. So let's say x is exponential with c. Remember, exponential random variables are positive, right? And their distribution is given like this. C e to negative cx dx, where x is positive. So in this case, we can calculate e to negative rx by e to negative rx times this distribution. Okay? And this is Riemann integrable and so on. So this is from 0 to infinity. I write it in the Riemann way. And what is the value of this integral? Well, if you don't like calculus too much, at least you know some distribution functions, right? Or distributions. So you can rearrange it as r plus cx dx. So this almost looks like the density of an exponential, but it misses its c plus r or r plus c, whatever. But unfortunately, we don't have this r plus c. Instead, we have c. So I can rearrange it this way. Now this is going to be just 1, so that the result is c over r plus c. So I just did it to show you the trick. Otherwise, it's an easy integral from a calculus point of view. Just the exponential function. But I think this trick still saves you some time, because when you do Riemann integration, you have to check the limit as this goes to infinity and so on. But this is just one shot. From 0 to infinity, this integrates to 1, because it's the density of an exponential with parameter r plus c. So this is for every r in r plus. So Does this look familiar to some of you? Do you remember any function like this from an undergraduate course? Exponential of a random variable. And you take expectation. No, like a transform or some related function. Moment generating function, right? So let's put a remark here, okay? So a related quantity, a related function is the so-called moment generating function. Which is defined on the entire real line without the negative sign here. So, well, this is always positive, right? This is an exponential function, so it's always positive. So it's between 0 and plus infinity. So one drawback of this function is that it may take the value plus infinity for many r. So for some type of distributions, this does not behave very well. But the Laplace transform behaves very well no matter what your distribution is. As long as you deal with a positive random variable, you can look at the Laplace transform, and it is always a finite value. Because e to rx and r can be positive or negative. So if r is positive, this is going to be like this, right? So x e to rx is going to be something like this, and it can explode to plus infinity. And in expectation, this can be the case. The expected value of this can be plus infinity. And if r is negative, again, doesn't save you, because now you have this part, because and people use it not for just positive random variables. I forgot to say that. This is used for real valued x. I forgot to say that. So there is no separation between the positive case and the general case. And this doesn't behave very well in general. So if you allow for negative values as well, you can again have some issues. So that's why we introduce Laplace transform instead, which at least works very well for positive random variables. But of course, if your random variable is positive and you look at the values of r that are negative, you get the Laplace transform, of course. OK. Any questions about Laplace transform? So of course, the question should be, why do we even deal with that, right? Is it as nice as generating functions? For instance, does it characterize a distribution of x? Okay? And the answer is yes. So it's going to be a big theorem. And the name of the theorem is Laplace transform determines the distribution of x. Okay? So suppose x is a positive random variable, like this, is a random variable. And let nu be a measure on r bar plus Borel r bar plus. So I'm not saying that this is the distribution of x, okay? This is a generic distribution. The following are equivalent. The following are equivalent. So number one is that x has distribution nu. In other words, probability that x is in D is given as nu of D for every D in Borel sigma algebra. And we already figured out a way to rewrite this last week, and it was the following. So we have e of expected value of f of x is given as f d nu for every measurable function f that is positive. So it is from r bar plus to r bar plus. Positive measurable, okay? So the integral is also over r bar plus. And what we're going to do is to put more structure here. So let me follow my order in my notes. Okay, bounded measurable for every bounded measurable function f from r bar to r. So I'm not assuming this is positive now. I'm just assuming it's bounded. So there is a lower bound and there is an upper bound on the values of this function. One more. F d nu for every bounded and continuous, okay, continuous function f from r bar plus to r. So you might ask how we can write this, because we haven't proved continuous functions are measurable, but I'm using it as a fact. So let's write it as a fact. Continuous functions are measurable. Continuous functions are measurable. Okay. Maybe later in the course, we're going to prove it. Anyway, so the last thing is about Laplace transform. Of course, so far, this is all variations of the second property, okay? It's just some more structure or continuity, etc. So now this is going to be the crucial one. So we have e to negative rx, the Laplace transform of x, is given as e to negative rx. Let me write it nu dx as nu dx because I have to put this x here. So this is for every r that is positive. So this is the statement of the theorem, and I need to add a second statement to the theorem as an in particular type of conclusion. The Laplace transforms of two random variables, two positive random variables, coincide, then they have the same distribution. And this is by 5 implies 1. So 5 says, if you know that the Laplace transform is calculated using this measure, then you know that this measure is indeed the distribution of x. So using 5 implies 1, you can conclude that if you have two random variables whose Laplace transforms are the same, meaning that e to negative r minus rx equals e to negative ry, okay? So let's say xy are positive, and we have e to negative rx equals e to negative ry for all r. This implies the distributions are the same for all d in the Borel sigma algebra. Okay. So let's look at this theorem, okay? Let's look at this theorem. What does it say? So the first statement is very clear, right? Just x has distribution nu. So if nu is the distribution of x, then we have that the probability that x takes values in this set is given as the measure, the value of the measure at d, right? This is precisely the meaning of being a distribution. And we generalized this from probabilities, or namely expectations of indicator type functions, to arbitrary positive measurable functions last time. So if you have this property for every Borel set d, then you also have that the expected value of an arbitrary positive measurable function of x, the expected value of an arbitrary positive measurable function of x is given as an integral with respect to the distribution. So 1 implies 2, and also 2 implies 1, because you can just take f to be an indicator function. You will get this property. So this we proved last time. Okay? So the equivalence of 1 and 2 is already shown. So 1 and 2 are equivalent, shown last time. Okay. So now 2 and 3, well, they don't really imply each other immediately, because in 2 you have positive functions, and in 3 you have real valued functions that are bounded. And boundedness is, of course, to avoid infinity minus infinity situation, right? Well, you can separate f into its positive and negative parts. So you can prove 2 implies 3, and you can also prove 3 implies 2. But I will leave it as a homework exercise. I already put it as a homework exercise. So let's say 2 and 3 are equivalent is left as an exercise. Well, if you look at 2 and 5, 2 deals with positive measurable functions, and 5 is also dealing with a positive measurable function, right? E to negative r of x is a positive measurable function, right? Exponential is always positive. So this is a positive measurable function. So 2 implies 5 is immediate. There is nothing to prove. Just take f equals e to negative rx, right? 2 implies 5. Immediate, just take f of x equals e to negative rx for each x, for each r. So if we can show 5 implies 4, and 4 implies 1, then we're done, okay? So 1 and 2 are equivalent, 2 and 3 are equivalent, 2 implies 5. We'd like to prove that 5 implies 4, and 4 implies 1. So that in this diagram you can go from every statement to every other statement. You can find a path, so the proof would be complete, because we would like to prove that the following 5 things are equivalent. Okay? So the core is really this 5 implies 4. I'd like to first prove the easier one. 4 implies 1. So let's assume expected value of f of x is given as f d nu for every bounded continuous f on R bar plus. And to show the distribution of x is nu, it is enough to show that the probability that x is less than z, which is just the expected value of 0 to z applied to x, it is enough to show this part. What is this part? Indicator of z, nu dz. Sorry, dx at x dx, which is going to be nu of this interval 0 to z. Show for each z, let's say, for each z. Because it's the cumulative distribution function of x, and if you know the cumulative distribution function, you know the distribution of x. And the mathematical reason behind this was, just to recall you, that those intervals 0 to z form a pi system that generate the Borel sigma algebra on the positive real line, okay? Or R bar plus, whatever. So the thing is that this function is not continuous. It is bounded but not continuous. If it were continuous, we don't need to even prove anything, because just in 4 we have bounded continuous ones. Here we have bounded discontinuous one. The issue is that this function is not continuous. So let me draw a picture. Z is here. So it is 1 when x is between 0 and z, and then it goes to 0. Okay? So that's the shape of this function. Let me write. Okay? So the idea is then to try to approximate this indicator function using bounded and continuous ones. Okay? So you have a discontinuity at z. How can you kill it? So if you had something, you wouldn't have this discontinuity. So can you make it a continuous function? Can you play with this a bit and make it a continuous function? Can you modify this function slightly and make it a continuous function? Again, make sure it starts from 1 and it decreases to 0 at some point, but make sure it happens continuously, okay? Not like a jump at z. How can you kill the jump at z? By slightly modifying the function. So you have discontinuity. Can I do this? Of course not, right? This wouldn't be a function. So what should I do? To make it what? Not vertical, but with a slight slope, right? So of course I cannot do this, but I can do this. let's say, to z plus 1 over n. And as n tends to infinity, you have z plus 1 over n tends to z. So your continuous functions will approach to this discontinuous function. Okay? So let's do it formally. I'm going to call it, let's say, Fn, okay? So for each n, define Fn of x as 1 when x is between 0 and z. It's going to be something, and then it's going to be 0 when, so after z plus 1 over n. After z plus 1 over n. X. And also I need to define it at plus infinity, so I include plus infinity. And here it's going to decrease linearly. So I calculated it. It's just, you just need to calculate what the value of this function should be to preserve this triangle. So I guess z minus x times n when x is after z and before z plus 1 over n. So let's see. When z is equal to x, when x is equal to z, I have 0 here, so this gives me 1. When x is equal to z plus 1 over n, I have maybe the other way around. This is correct? So if x is equal to z plus 1 over n, z minus x is minus 1 over n. Maybe the other way. Maybe I should put a plus here, and this is done, right? Anyway, we don't even need to figure this out. Just find it yourself, right? Better. But the picture is clear, right? Just find this value here when x is between z and z plus 1 over n. Anyway, so Fn is bounded continuous. So by what we assumed, which is number 4, we have Fn of x is given as Fn d nu for each n. And since these are bounded by 1, so we have Fn of x is bounded by 1, and Fn is bounded by 1. So by bounded convergence theorem, which is a special case of dominated convergence theorem, so bounded convergence theorem, when you let n go to infinity, you get, so the limit of Fn's applied to x is given as limit of Fn's d nu, and the limit of Fn's is just our indicator 0 to z. And that's what we wanted to show, right? Expected value, indicator 0 to z applied to x, integral, indicator 0 to z with d nu. So this is what we wanted to show. So 1 follows. So all we have to show is the most difficult part, which is 5 implies 4, and we're going to leave it for the next hour.